Hello, here's another mathematical part of this tutorial, this time on stochastic games. This is an extension of controlled Markov chains, so I'll mainly speak about controlled Markov chains and then say a little on how they extend. This will allow us to present the dynamic control of advertisement in social networks. We have already seen a little bit about Markov chains. We now look at their control. And this will add some new objects and some complexity. So in addition to a state space, we have here action spaces. At each state there may be another set of actions available. Everything here is assumed to be finite. So the state space is finite, and the action state is either finite or convex and compact. The transition probabilities that we had before are now more complex. They now depend also on a parameter, which is the action that is taken. We further introduced immediate costs or immediate rewards. It depends whether we minimize or maximize. We define information and strategies that may depend on this available information. We then introduced cost criteria to minimize or to maximize, if we speak about payoff, over subsets of different types of subsets of policies. We shall consider here discrete time in this part of the talk. So time is slotted and all slots have equal lengths. We now go into more details in describing the different objects. So first the states. So we assume that we still have the Markov property. So the state at time t contains all the information that determines the future evolution for a given choice of a control at that time and in the future. In that sense it's Markovian. In general the process does not have to be Markovian, but in that sense it is. We denote by A of x the set of actions available when at state x, and by pxay the probability to move from a state x to a state y if we use an action A. We now define histories and strategies. A history is a sequence of all previous states and previous actions as well as the current states. A strategy or a policy is a set of probabilities conditioned on observed histories. So a given strategy U is a sequence U1, U2, and so on, where each of these U, so U of t, is the probability of choosing different actions for an observed history of length t. And this is the probability that is going to use when choosing actions at time t. This class of policies is very large, so we define subclasses of policies that are simpler in the way of describing them and in the way of implementing them. So we are first interested in a class of Markov policies, which are decisions that depend on the whole history only through the current time and the state at the current time. A set of policies is called stationary if it depends only on the current state. It doesn't even depend on the time t. So it is homogeneous in time. The probability of choosing different actions when observing a given state is the same over time. We denote by UM the set of Markov policies and by US the set of stationary policies. Now, if one uses a Markov policy, then the whole state process becomes a Markov chain. If one further uses a stationary policy, which is a subclass of Markov policies, then the state process is a homogeneous Markov chain. We shall also introduce the stationary deterministic set of policies, USD. in which the choice of different actions at different states does not involve randomization. So we choose, it's like these policies are like tables. They say, we are at state X, okay, this is the action which is a function of X that we shall use. So there is no randomization here anymore. There are various criteria of interest, and maybe we shall see others later. But for the time being, I'll define the total cost criteria or the total reward criteria, and then later the expectation of this total reward criteria. So we define some running costs, which is a function of pairs of actions and states. This is the R there. And a final or a terminal reward, which is a reward that is a function of the state at the final time t. This final time t might be random. For example, it may be the time at which we reach some given set of states. So the summation of these over time, of the running costs or the running reward R over time, plus the terminal cost, is total sample cost. And we are especially interested in the expectation of this. So we want to maximize its expectation. So more precisely, we want to find a U that achieves the supremum of Vxtu, where Vxtu is the expected sample cost, or the expected sample reward in this case, given an initial state X and a policy U that is used, and a horizon of length t. A key role will play the dynamic programming formulation that we shall use later on in the dynamic control of advertisement. So the optimal value turns out to satisfy the following recursion. So the expected total reward at time when there is t plus 1 time to go, when the horizon is of length t plus 1, and when the initial state is x, is given as the maximum over the actions A that are available at state x of the following summation. The first term is just the reward at the x when using A. And the second is what is called the cost to go. So it is the summation over y of the transition probabilities to y, weighted by the value v at y at time t. So you see the left-hand side of the equation is the cost for a horizon of length t plus 1, and it is given recursively as a function of the right-hand side of the equation, which involves v at time t. So this is a way that allows, we can use this in order to calculate the optimal value of the control problem. Now let the set, introduce the set A of x and t plus 1 as the set of actions that achieve the maximum in the above dynamic programming equation. So since this dynamic programming equation is a function of x and t, then also this set that achieve the maximum can be, in general, can depend on these x and t. So what we know is that V is the unique solution of the dynamic programming. So the optimal value, the maximum expected reward, satisfies this recursion. And any Markov policy that achieves the max is optimal. We shall now turn to infinite horizon dynamic programming. So in infinite horizon dynamic programming, in fact, we get it as the limit as t goes to infinity of the previous one. And then v of t and v of t plus 1 is the same object. So instead of getting a recursive equation, we now get a fixed point equation where Vx is in both sides and it's not a function of time anymore. So we get again that Vx is the function of the fixed point equation. Vx is the maximum over the actions available at x of the summation between the immediate reward Rx of A and the sum of Vy's weighted by the probability to go there when using A from state X. So it's exactly what we had before, but now it's not a recursion anymore. If A of X are the set of actions that achieve the max, then we say the following: a stationary policy for which Ux is in Ax is indeed optimal, and we know that any solution to the above equation is optimal for the original problem. We shall be using, in fact, a random horizon. So T will be the time to reach some set Z of states in our case. And we define this T to be infinite if we never reach this set. So with these definitions, the previous theorem still holds. So we can still compute the value of the controlled Markov chain as the unique fixed point of the previous equation that we saw. In the formulation that we shall use, time will turn out to be random, whereas the theory that I've been showing so far was for discrete time, so for equal time slots. So we'll have to modify what we did so far, or to extend what we just saw, to random time between transitions. So now consider the same controlled Markov chain. So the Markov chain with the same transition probabilities as we had before, and introduce Tn to be the time of the nth state transition, the nth time that we move from one state to another. Let capital N be such that T of n is capital T. So capital T is the time at which we reach some random set of states. So n will be the index of the transition in which we reach this set of states. Then we have a controlled Markov chain which is said to be embedded at times Tn. So we just look at a discrete process that we obtained at time Tn. This process turns out to be also a controlled Markov chain, with xn being x at the nth transition, and an the action that we choose at the nth transition. So if we define the costs just as the reward, as the sum of the rewards at the transition times, and this is a well-defined object, and we can apply the previous results. The only problem is that this cost doesn't have much meaning. It's not a meaningful cost for several reasons. First, it is a function of the action just at the moment of the transition, and it completely ignores the actions that will be taken between transitions when computing the costs. Secondly, there is a problem with the fact that it doesn't take into account the length of transition. So if we are in a state which is very, very expensive, but we stay very, very little time, it will not distinguish between this and another one in which we pay the same thing, but we stay a very long time. So we should use another cost than this one. But we would like to use this one because we have a theory for this cost. we know how to compute the optimal control for this cost. So let's see how we solve the two problems. The first problem can be solved, of course, if AT remains constant between transitions. And this is the case if we use a stationary policy or if we use some other policy that takes them to be constant. And this can be done, in fact, without loss of optimality. I will not show this here why we may restrict to such policies, but this turns out to be the case. Now, the second problem was that at different state we might stay at during longer or shorter times than in others. This problem would not exist if the times were independent of the state and of the action. So if the times were IID if they had the same distribution and were independent of xn and of an. So the meaningful cost that we should have if transition times are random is to replace the summation over the slots now by an integral over time of the reward plus the terminal reward, and take the expectation of this. Now, first thing that we can do, we can write it in a discrete way by replacing the integral between 0 to t to a summation of integrals, and each one of the integrals in the summation is the integral from a given transition to the next one. So we write these as S of n. So Sn is the cost, the cumulative cost from time tn till time to transition tn plus 1, or the cumulative reward. And we consider stationary policies so that x and t and a and t do not vary between two transitions. So we can write them as x of n and a of n for transition n. Now, if the expected transition time were 1 for all states and actions used, then we would get the same expression as before for the expected total reward. So the summation over these integral costs from a transition to another over all capital N transitions are just equal to the summation of the rewards at the transition instance in expectation. Why? Because the expectation of the integral of some variable which is constant is simply the expectation of this variable times the expected duration on which we integrate. Now, the fact that the expectation can be written as a product of expectation holds because we assumed independence. The methodology that we shall use will turn out to work very well because our model will involve exponential random variables. So I would like to cite two properties that we shall use for exponential random variables. Consider an IID sequence, T of I, of exponentially distributed random variables, each with the same parameter L. And let n, capital N, be geometrically distributed with parameter P. So the probability that n equals y is simply P times 1 minus P to the power of I minus 1. Then it turns out that the geometric sum of Ti, so the summation of I going from 1 to capital N, which is geometrically distributed, of the IID variables Ti, has also an exponential distribution with parameter P times L. So to conclude, a geometric sum of exponential random variables is also an exponential random variable with a longer expectation, or with a smaller rate. Exponential time between transitions. Here's the next slide on this issue. So assume that one can go from state x to any state y in the set S of x. And now we assume that transitions here are exponential. So the time txay till the transition occurs to state y, if an action A is used, is exponentially distributed with parameter L of xay. Now, I was just talking about a given transition. But if any transition, if you want to know when any transition occurs, so it turns out that the first transition, just by definition, it will be at time which is the minimum over all y of the txay. The special thing about exponential distribution is that the minimum between independent exponential distributed random variables is also exponentially distributed with the sum of L's of rates, or with the sum of parameter as the parameter of this new variable. So after these two slides, I'm ready to introduce uniformization. So we saw that it is needed that the time till next transition shouldn't depend on the state and action. So we need L, X, and A just to be constant over all X's and over all A, which will not be the case in our problem. So what we do, we change both the times between transitions and the transition probabilities in a way that the transition process itself is unchanged. But yet, in the new process, L becomes constant. And this is done simply by adding a rate of transitions from a state to itself. Okay, so here come more details on this. So assume we have at state 1 a rate L1 of transitions to some set Z1 of states, and at state 2 we have a rate L2 which is larger than L1 to some other set of states Z2. The time till the next transition to Z1 from the state 1 occurs according to an exponentially distributed random variable with parameter L1. And we wish it to change this to L2, which is larger. So first define P as the ratio between L1 and L2. So P is smaller than 1, it's some probability. We shall now use the same rate of transition L2 in both states, but in state 1 we shall add the transitions from state 1 to itself. These type of transitions are called fictitious transitions. We set them to occur at a rate of L2 minus L1. Thus, at state 1, the total rate of transition is now L1, the original ones, plus new transition to the same states that occur in a rate of L2 minus L1, and this gives us indeed L2 as the total rate as we wanted. Now, why does it work? Why does this give us the same process of transitions as before? Or by that I mean that it gives the same process of transition to states other than 1. Because in both cases, when you go from a state to itself, I don't call this a transition. I don't call a fictitious transition a real transition. So let's see why it works. Each time a transition occurs from state 1, the probability it is to the set Z1 is now P. With probability 1 minus P, it's a fictitious transition. The time between transitions from state 1 is exponentially distributed with parameter L2 after the transformation that we did. Thus, the time till there is a transition to Z1 can be written as a sum of n IID exponentially distributed random variables with parameter L2, where n is now geometrically distributed with parameter P. So there is a sequence of transitions which are from state 1 to state 1, and after a geometric number of these, the transition is successful to the set Z1. So we have this geometric number of transitions till we reach Z1. And each one of these transitions is exponentially distributed with parameter L2, because it is the minimum between the time till a transition to Z1 is exponentially distributed with parameter PL2. And PL2 is just L1, which we had before. So indeed, the real rate of transitions to Z1 did not change by adding these fictitious transitions. Here's an extension to stochastic games. So we extend the problem of controlling a Markov chain to controlling it by several players or several controllers. Now, a stochastic game is this extension for several controllers in which each one of them wishes to maximize its own expected utility. So now we'll have a vector of utilities, one for each controller, and each one wants to maximize its own. The definition of state and history is unchanged. Actions are now replaced by vector of actions, so one for each player. But this vector of action can be viewed as a vector action, as one action which is a vector, in terms of transition probabilities. So the definitions of strategies and cost criteria are trivial extensions of those that we had before. And the definition of an equilibria, which is now the solution concept, is as we had in non-cooperative game in our first part in this tutorial. A few words on the extension of the dynamic programming part to a game. I now introduce dynamic programming. In our setting, it turns out that there exists an equilibrium within stationary policies. But when restricting to stationary policies for all players, then the best response is in fact a controlled Markov chain, whose transition probabilities depend on the policies of all other players. Therefore, any solution of the fixed point equations is a value for the game, and the corresponding argmax is an equilibrium. So now, instead of having dynamic programming for one player, we have n dynamic programming where each one describes the best response. All equations are achieved here with equalities. Here are some comments. First of all, why are the dynamic programming so useful? Well, there is a maximization there, and there is a maximization in the initial problem. But the maximization of the initial program is over the set of all policies, which is exponential, an exponential set in terms of in terms of the size of the states and action spaces. Whereas the dynamic programming, it is a maximization over the action sets. Now, when considering equilibria in the game formulation, a pure equilibrium does not exist in general. The maximization for a player I is thus over the set of probability distributions over his action set, instead of just directly over his action set. It turns out that if we take the maximization over probability distributions, instead of taking them over directly over the actions, then we can indeed obtain a stationary policy which is in equilibrium. Before we finish, I would like to show you a slide on state aggregation, which will be a very important one later on. So the question is whether we can aggregate set of states into one state. So we have several aggregates like this, S1, S2, until SR. When is it possible to aggregate them into one state? So first of all, these sets have to be, within each one of them, states have to be indistinguishable in the following sense. The same transition probabilities from any state within Si to any global set of states, Sj, any group of state. So the transition probabilities between any x within any of the Si's to any other Sj has to be the same. Secondly, the same immediate reward or cost has to hold for every state in such a group. And finally, we need the same available actions. If this holds, then we can transform the problem into one with a lower dimensional state space. Now, why does it work? Well, if we look at the process that tells us in which of the aggregates we are, we'll see that it is in fact a controlled Markov chain. It satisfies the structure that we define on the controlled Markov chain. And therefore, by giving more information, we cannot get anything better because we already know that the controlled Markov chain theory provides us optimal policies. Now, what about stochastic games? If all other players use aggregate policies of this type, then we are faced with a controlled Markov chain, a standard one, or an aggregated one if we also consider each one of the possible aggregate as a state. Since it satisfies the structure we did, I mean by that since it is a controlled Markov chain, then the best response, there will be a best response among those policies. There are a lot of references on controlled Markov chains, but there aren't so many on total cost problems. I recommend my own book on that. It doesn't include, though, exponential times between transitions. And what I showed you about that you can find in a paper by Stephen Lippman, which is called Applying a New Device in the Optimization of Exponential Queuing Systems.